Okay, next we want to talk about pH and pKa, which are two of probably the most important values in all of acids and bases. So how can we measure acidity? Well, there are two measurements involved with acids and bases. The common one is pH. This is the acidity or basicity of a solution, right? If you have a solution of some kind of liquid and you wanted to measure how acidic that solution is, you would use pH. pH 7 means that the solution is perfectly balanced. If you have a pH less than 7, means it's acidic, and the further away it is from 7, the closer it is to 0, the more acidic it is. So a solution with pH of 1 is more acidic than a solution of pH 6. And higher than 7 means it's basic. Again, closer it is to 14, the more basic it is. So pH 13 is more basic than pH 8. A pH 4 a liquid solution of pH 4 would mean that the dissolved in the liquid is more acid than base, and so the solution as a whole is slightly acidic. It doesn't mean that there's only acid in the solution, right? It means that there's acid. It could mean that there's acid and there's base, and when you combine all of that together, overall it's more acidic, and so you get an acidic solution. Electrophiles are base electron donors. Electrophiles, does it say that? May have mistyped that, yeah. Yeah, I may have mistyped that then. These might be switched, right? Because electrophiles are electron acceptors and nucleophiles are electron donors, yeah. Sorry about that. So I will actually make sure in the slides that that is correct. So I'll reiterate again. Nucleophiles are electron donors. Electrophiles, I'll do it in a different color. Electrophiles are electron acceptors. Thank you for catching that. Back to what I was saying. So again, pH 4 liquid may have more both acid and base, just more acid than base. So that's why it's overall more acidic, or higher concentration of acid than base. And essentially what pH is a measure of the concentration of H+, right? That's what the H in the pH stands for. So if you have a lot of H+, it goes down to close to 0. So what pH 4 means is that there's a lot of H more so than there is OH minus, or because this kind of uses the Arrhenius definition. So pH and pOH always together make 14. So if you have pH of 4, it means you have a lot more H than you have OH, essentially. Okay, moving on. So the other measurement that we use to measure acidity and basicity is pKa. There's also pKb, but that's rarely used. Mainly we use pKa, which measures the acidity, and it refers to the acidic strength of a compound, right? A specific molecule, rather than a solution as a whole. The lower the pKa, the stronger the compound is as an acid. Similar to pH. If you have a lower pH, you're more acidic. pKa kind of goes by similar rules. If something has a very low pKa, that means it's very acidic. For example, the pKa of HCl, which you know is a strong acid, is about -6, so it's a very strong acid. Technically, once you go below 0, you can't really tell, like, experimentally. This is more hypothetical with the negative pKa's. It's more hypothetical because you can't actually go below. You can't actually have negative pKa's experimentally, but people have found out how to do it mathematically or theoretically. And what a negative pKa means is just like really acidic, like a really strong acid, like for example HCl. The pKa of acetic acid, which is the other acid that I was commonly using today's lecture, it's a weak acid, and it has a pKa of about 4 to 5, right? And it varies sometimes, but it's about 4 to 5. So it's a weaker acid, and it's actually classified as a weak acid. CH3NH3 plus, which is the conjugate acid. Like I mentioned, it's an acid. It's conjugate acid of a base. It has a pKa of about 11. The reason it's such a weak acid is because NH2 plus is a relatively strong base. So relatively strong base, conjugate acid, relatively weak. This conjugate acid has a pKa of about 11. Okay. And there's actually a specific reason why I picked these two specifically to show you the pKas of the 4 and the 11. It's because these are very commonly used in actually on the MCAT, because these are the exact two compounds that make up amino acids, right? So this and this are the amino end of the amino acid, and this is the acid part of the amino acid, right? And you'll actually have to memorize these pKas for when we talk about amino acids this Saturday, I believe. But we'll cover that more on Saturday. But you should know the pKa of this is 4 to 5 about, and the pKa of this is about 11, right? Okay. So what does all this mean? Well, pKa really refers to the pH at which the concentration of acid is equal to the concentration of base of that one compound. Great equation to know is the Henderson-Hasselbalch equation. I believe for the MCAT, you're technically not required to know this equation, but just like I don't think you were technically required in most undergraduate general chemistry courses, but it was very, very highly recommended because this can help you understand it much better, and it can be very useful in solving acid and base problems that you may encounter, even if it's not required. Okay, so the Henderson-Hasselbalch equation is this. This is for acids, and this bottom one is for bases. You'll only really be using this top one. I don't really think you'll ever use the bottom one, but just in case you want to learn it. So pH equals pKa plus log concentration of base over concentration of acid. So what I mentioned was pKa is the pH at which the concentration of the acid and the conjugate base are equal. So for example, I mentioned that for NH2 and NH3, right, the pKa is 11. So at pH is 11, they're in the solution of just these molecules, half of the molecules will be in this form, and exactly half of the molecules will be in this form. So you never really see in a solution everything's only in acid form, or everything's only in base form, all of the molecules, or all of the atoms are all in base form, or all of the atoms are all in acid form. What you usually see is a mixture. But typically it's very favoring one side. So when we say it's in the acid form, it's because 99.9% of all the molecules are in acid form and very few are in base form. However, when the pH is equal to the pKa of the specific compound, which here we mentioned 11, at pH 11, exactly half of all of the molecules here will be NH2, and exactly half will be NH3 plus, right? And the reason I said the Henderson-Hasselbalch equation is kind of useful for seeing this is because you know concentration of base and concentration of acid. Like I mentioned, when the pH is equal to the pKa, they're equal. So whatever is on the top is here on the bottom. So this essentially means that pH equals pKa plus log of 1, right? Because anything divided by itself is 1. So log 1. You know that log of 1 is 0, right? So it's just pH equals pKa plus this whole thing is 0. So pH equals pKa, right? That's how you mathematically prove it. And this is also very helpful for determining pH if you know that there's more base or acid, right? If you know that there's more base, you'll have more here on the top, less here on the bottom. You'll have like a positive number, so you'll have like 1.5 or something. Here maybe log of 1.5 is some positive number. I don't know what it is, but it's some positive number. So the pH is slightly higher than the pKa, for example. And that makes sense because there's more base than there is acid. Whereas if you had more acid, log would be, it would be like log 0.8, 0.8. Log of a decimal less than 1 is negative. So it would be minus, so it would be pH equals pK minus a number, which is always less than, right? And same thing can apply for these, but like I mentioned, you don't really see this. And this just uses pKb, pOH, and the acid and base are flipped. Right, notice that. Keep track of that. So how can we use all this information, right? We know that for any molecule, if it is a stronger acid than the other molecules around it, it will act as an acid and will donate a proton and thus become deprotonated. So again, we know examples. So if you have HCl, which you know is a strong acid, and it's surrounded by water, right? If you throw some HCl into some water, the HCl is obviously a stronger acid than the water. So it will act as an acid and it will donate a proton to the water. When HCl donates its proton to water, it becomes deprotonated into Cl minus. It gets deprotonated, it becomes Cl minus, and the water becomes protonated because the water acts as a base. And it becomes H3O plus, right? Because it gets a proton, right? And that makes sense to you guys, right? Obviously, Cl is a stronger acid than H2O, so it will act as an acid and it will force H2O to act as a base. And vice versa would also work if you put in a strong base like NaOH into water. It will accept a proton and it will turn the water into OH minus. Okay. We also know that pH is a measure of the acidity of a solution or the amount of acid relative to base in that solution. Therefore, if you drop a molecule into solution of known pH, you can probably tell whether or not it will act as an acid. So the general rule is if the environment is more acidic than a molecule, the molecule will not act as an acid and will remain protonated, right? It will act as a base. But since it's already in its base form, it will just stay the way it is. If it is more acidic, it will act as an acid and deprotonate, and it will change. And this I would highly recommend you to either take a picture of or memorize. If the pH of the solution is greater than the pKa of the molecule, then the molecule becomes deprotonated and acts as an acid. If the pH of the solution is less than the pK, then the molecule is protonated, right? If it's an acid, it stays in its regular form. If it's a base, it will act as a base, right? And this could actually work for both acids and bases because bases will have a really high pKa, right, usually. And if the pH of the solution is greater than that, which is very rare, then the molecule will be deprotonated. So bases will almost never, if it's a strong base, it will almost never be deprotonated because the pH of the solution just won't be higher than its pKa, right? If you have a pKa of like 20, there's no pH that can be higher than that because the pHs stop at 14. So it'll pretty much be deprotonated in any pH. Whereas if its pH is less than the pK of the molecule, then it's obviously protonated. Please take a minute, answer this question, let me know. Okay, I'm gonna close the poll. And if you didn't get your answers in on time, that's fine. Okay. So actually the results were very mixed. About an equal number of people picked D and C, with B being not actually far behind. I would say the answer is actually B. And we can go over exactly why that is, okay? So we mentioned that if the pH is less than the pKa, that means the environment is more acidic than the actual molecule. If the environment is more acidic than the molecule, then the molecule will be protonated. I'll just write plus for protonated. Doesn't necessarily mean it has a positive charge, which means that it's protonated. And if the pH is greater than the pKa, that means the molecule is more acidic. It will act as an acid, and it will give up its proton. Doesn't necessarily mean, again, it has a negative charge. It just means it. I'm just writing negative to show that it's deprotonated, right? Okay. So let's look at each one individually because I gave you the pKas of all of them. Over here, I told you that the pH is 5, so pKa is 9.47. Well, pKa is greater than pH, therefore it stays this way. It stays exactly the way it is here with a positive charge because it stays protonated. 4.07, well, pKa is less than pH, less than 5, negative, so deprotonated. So normally it would have an H onto here on this hydrogen, but on this oxygen, but it doesn't because it's deprotonated. Stays exactly the way it is. So right now we have one positive charge, one negative charge. I'm just going to cross them out because they cancel out to make neutral. Over here, again, pK less than pH, this stays negative. Over here, pK is greater than pH, therefore it stays positive. Again, positive, negative cancel out. Now we get to these ones, right? Well, this has a pKa of 6, whereas the pH is 5. pH less than pKa is positive, right? So it should be protonated. Well, where would the protonation lie in these? Maybe here, right? This has a site for a proton, for a hydrogen, but look if there are any other sites where it could be protonated, right? And actually, there are. The protonation in this case, and this is called histidine. It's an amino acid that you will have to memorize. All of these are actually amino acids that you will have to memorize. You also have to memorize all of their pKa's, right? This is called histidine with a pK of 6, which you should memorize, and you should memorize what it looks like roughly. It actually has, if it was in acidic form, it would actually look like this, where the N would be positive, and it would have an H on the end, on this end specifically, right? Because it has a double bond, which can very easily form, which is kind of reactive, I should say, right? And so it can get another H and become positive. So at pH 5, it actually is protonated, meaning that it has this back, and it's actually +1 +1 for a total of +2.